I'm very glad you're here tonight. Before we get comfortable with tonight's science, let me know where in the world you're watching from. Maybe you're already tucked into bed, relaxing on the sofa, listening through headphones somewhere quiet, or simply winding down after a long day. Wherever you are, I hope you can get comfortable and let your mind wander for a while. And if these slower, relaxing science videos help you switch off, learn something new, or simply make the end of the day a little more peaceful, then liking the video and subscribing genuinely helps a lot. It gives the channel the support it needs to keep growing and allows me to keep making more of these sleepy journeys into science. And if you're already subscribed, thank you. Your support really does make a difference, and I'm incredibly grateful that you keep coming back. If you'd like to take these journeys with you beyond the screen, there's a Sleepy Scientist ebook waiting for you too. You'll find a QR code resting quietly in the corner for the first few minutes of tonight's video, or a link in the description whenever you're ready. And we're now uploading episodes to Spotify as well, so if you'd rather let your screen go dark and simply drift with the sound of the science, you can find us there and close your eyes completely. Tonight we're shrinking everything down about as far as modern physics knows how to go. Because beneath atoms, beneath protons and neutrons, and beneath almost everything we normally think of as matter, physics has uncovered a surprisingly small collection of fundamental particles. Quarks, electrons, neutrinos, photons, gluons, the Higgs boson, and a few quiet companions that complete the set, what we call the Standard Model. Just 17 particle types, together with the fields and interactions connecting them, are enough to describe almost everything we can directly see around us. Not quite everything, though, because as remarkably successful as the Standard Model is, there are still some rather enormous pieces of the universe that it cannot explain. So let's begin. How did just 17 particles come to build almost everything we know? Everything we can see around us seems complicated almost beyond comprehension. A glass of water contains an unimaginable number of atoms. A human body contains trillions of cells. A planet contains oceans, rocks, gases, metals, and living things. Stars burn for billions of years. Galaxies stretch across distances that are difficult even to picture. And the observable universe contains structures on a scale so enormous that ordinary intuition quickly gives up. And yet, when physics looks beneath all of this complexity, the list of known fundamental ingredients becomes surprisingly short. The framework that organizes those ingredients is called the Standard Model of Particle Physics. It is one of the most successful scientific theories ever constructed, describing every known elementary particle and 3 of the 4 fundamental interactions of nature with remarkable accuracy. Those 3 interactions are electromagnetism, the strong interaction, and the weak interaction. The 4th fundamental interaction is gravity. Gravity is enormously important on the scale of planets, stars, and galaxies, but it is not included within the Standard Model. Instead, gravity is described separately by Albert Einstein's general theory of relativity. Within the Standard Model, physicists commonly speak of 17 fundamental particle types. 6 of them are quarks. These are called the up quark, down quark, charm quark, strange quark, top quark, and bottom quark. Another 6 are leptons. These are the electron, muon, tau, electron neutrino, muon neutrino, and tau neutrino. Then there are 4 categories associated with the fundamental interactions described by the model. These are the photon, the gluon, the W boson, and the Z boson. Finally, there is the Higgs boson, an excitation of the Higgs field that plays a central role in giving many elementary particles their masses. That gives us the familiar total of 17. There is a little subtlety hiding inside that neat number. Nature rarely seems particularly interested in keeping diagrams tidy. There are actually 8 distinct gluon states associated with different combinations of color charge, but these are normally grouped together as one particle type when the Standard Model is presented in its familiar 17-particle form. Likewise, the positively charged W boson and negatively charged W boson are usually treated as members of the same W boson family rather than counted separately. so 17 is best understood as a useful way of grouping the known elementary particle species rather than a literal count of every possible quantum state. The word elementary is important as well. An elementary particle is one for which experiments have found no internal structure. As far as present measurements can determine, electrons and quarks are not little containers made from even smaller confirmed pieces. They behave as fundamental excitations of quantum fields. A proton, by contrast, is not elementary. It contains quarks and gluons. A neutron is also composite. Atomic nuclei are combinations of protons and neutrons. Atoms contain nuclei surrounded by electrons. Molecules are built from atoms, and from there the layers of complexity continue upward through cells, organisms, planets, stars, and galaxies. In that sense, almost everything familiar is composite. There is also an important qualification to the idea that 17 particles built everything. Most stable ordinary matter does not require all 17. The protons and neutrons inside atomic nuclei are constructed primarily from up quarks and down quarks, along with the gluon fields and quark activity inside them. Electrons then surround those nuclei and allow atoms to form. So the chair beneath you, the air around you, the oceans, mountains, planets, and your own body are built overwhelmingly from up quarks, down quarks, and electrons. The other particles are still essential to the deeper description of nature. Some govern interactions, some appear in radioactive decay, some are produced inside stars, in cosmic rays, or in high-energy collisions. Others existed abundantly when the universe was much hotter and denser. The Standard Model divides these particles into two broad families called fermions and bosons. Quarks and leptons are fermions. These are the particles usually associated with matter. Fermions obey the Pauli exclusion principle, which prevents identical fermions from simply piling into the same quantum state. That rule becomes enormously important when matter forms atoms and larger structures. Bosons behave differently. The photon, gluon, W boson and Z boson are associated with the electromagnetic strong and weak interactions. The Higgs boson belongs to a different kind of field, the Higgs field, which fills space and influences the masses of fundamental particles. Beneath all of these particle names lies an even deeper idea. Modern particle physics does not ultimately describe reality as a box filled with tiny hard beads. It describes a collection of quantum fields extending through space. What we call particles are excitations of those fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. A Higgs boson is an excitation of the Higgs field. The scale involved is almost absurdly small. Experiments have found no measurable size or internal structure for elementary particles down to distances far smaller than roughly 1/10,000th the measured size of a proton. And somehow, from physics operating at these extraordinary scales, the universe builds structures spanning billions of light years. The real achievement of the Standard Model is therefore not simply that physicists managed to produce a list of 17 names. It is that a remarkably compact set of quantum fields and interaction rules can explain an enormous amount of what happens around us. Radiation, atomic structure, nuclear reactions, electricity, chemistry, radioactive decay, and much of the physics taking place inside stars can all be traced back to this surprisingly small collection of fundamental ingredients. 17 particle types may sound like a modest inventory, but given enough space, enough time, and the rules of quantum physics, they are capable of producing a universe of almost ridiculous complexity. For a very long time, the atom seemed like a natural place for the search for fundamental matter to end. The word itself comes from the ancient Greek idea of something that could not be cut any further. Philosophers such as Democritus imagined that matter might ultimately be composed of indivisible pieces, tiny units beyond which there was nothing smaller to find. For most of history, this remained philosophy rather than experimental science. But by the 19th century, atoms had become central to chemistry, and scientists increasingly treated them as real physical objects rather than convenient bookkeeping devices. Then, the supposedly indivisible atom began to come apart. In 1897, Joseph John Thomson was studying cathode rays, mysterious streams produced inside evacuated glass tubes. By observing how these rays were deflected by electric and magnetic fields, Thomson concluded that they were made from particles carrying negative electric charge. These particles were eventually called electrons. The discovery immediately created a problem for the old idea of the atom. If an atom contained electrons, then an atom could not be truly indivisible. Something smaller was already hiding inside it. At first, scientists had only a vague idea of how the pieces might be arranged. Thomson proposed a model in which negatively charged electrons were embedded within a diffuse region of positive charge. That picture did not last very long. A dramatic change came from experiments associated with Ernest Rutherford and carried out by Hans Geiger and Ernest Marsden. They fired alpha particles at extremely thin sheets of gold and watched how the particles scattered. If positive charge were spread smoothly throughout the atom, most alpha particles should have passed through with only gentle deflections. Most did, but a tiny fraction bounced through surprisingly large angles. Some were even scattered almost directly backward. Rutherford later described how astonishing this result seemed. It suggested that almost all of the atom's positive charge and much of its mass was concentrated in a region far smaller than anyone had expected. The atomic nucleus had entered physics. The atom was now understood as mostly empty space, with a tiny central nucleus surrounded by electrons. On the scale of the atom, the nucleus was extraordinarily small. If an atom were expanded to something approaching the size of a stadium, its nucleus would occupy only a tiny region near the centre. The nucleus itself soon proved to be composite as well. Protons provided the positive charge, but atomic nuclei could not be explained using protons alone. In 1932, James Chadwick discovered the neutron, an electrically neutral particle with a mass similar to that of the proton. For a brief and rather peaceful period, the basic inventory of matter looked wonderfully simple. Electrons lived outside atomic nuclei. Protons and neutrons lived inside them. Perhaps that was all nature required. Nature, unfortunately for anyone who likes shortlists, had other plans. Only months after the neutron was discovered, Carl Anderson found something completely unexpected while studying cosmic rays. He observed a particle moving through a magnetic field with the same mass as an electron, but the opposite electric charge. This was the positron. Its existence had been predicted through the relativistic quantum theory developed by Paul Dirac, but Anderson's observation transformed antimatter from a strange mathematical implication into a real part of nature. Particles now seemed to come with mirror partners, and the list was only beginning to grow. Cosmic rays continually strike Earth's atmosphere at high energies, creating cascades of secondary particles. These natural collisions became an early source of discoveries, revealing particles that do not normally survive for long in ordinary matter. One of the first surprises was the muon. The muon behaved rather like a heavy electron. It carried the same electric charge but had a mass more than 200 times greater. Its discovery was puzzling, because nothing in the existing picture of atoms seemed to require it. Then came still more particles. Pions appeared. Kaons appeared. Lambda particles appeared. As accelerator technology improved, experimental physicists found a steadily expanding collection of short-lived particles and resonances. By the middle of the 20th century, the tidy world of electrons, protons, and neutrons had turned into what physicists sometimes called the particle zoo. The name was appropriate. There seemed to be an entire menagerie of new particles, many with strange masses, charges, lifetimes, and decay patterns. One major clue had already been suggested by Hideki Yukawa. In the 1930s, Yukawa proposed that the force binding protons and neutrons inside atomic nuclei could arise through the exchange of a new particle. he predicted that such a particle should have a mass somewhere between that of the electron and the proton. The particle later identified as the pion fitted naturally into the description of the residual strong interaction acting between nucleons. But pions themselves did not turn out to be fundamental, neither did many of the other newly discovered particles. The real simplification arrived when physicists began to notice patterns. Murray Gell-Mann and Yuval Ne'eman independently developed a classification scheme known as the Eightfold Way. Instead of treating every newly discovered particle as an unrelated curiosity, the Eightfold Way arranged many strongly interacting particles into families according to properties such as charge and strangeness. The organization resembled a kind of hidden periodic table. Particles that had looked random began falling into orderly mathematical patterns, and patterns in physics often suggest underlying structure. In the early 1960s, Murray Gell-Mann and George Swake independently proposed that many particles believed to be elementary were actually made from smaller constituents. Gell-Mann called them quarks. The original model began with 3 types, now called the up quark, down quark, and strange quark. More quark varieties would later be discovered, but the central idea was already powerful. Protons and neutrons were not fundamental. Pions and kaons were not fundamental. Many inhabitants of the particle zoo could instead be understood as different combinations of a much smaller number of underlying particles. A proton, for example, could be described by 2 up quarks and 1 down quark. A neutron could be described by 1 up quark and 2 down quarks. Mesons could be understood as combinations of a quark and an antiquark. Suddenly, what had looked like uncontrolled complexity began to collapse into a simpler structure. Experiments gradually strengthened the case. High-energy scattering revealed point-like constituents inside protons. New quarks were discovered. Theories of the strong and weak interactions improved. Quantum field theory provided the deeper mathematical language needed to describe particles not as miniature solid objects, but as excitations of underlying fields. The emerging picture drew together several enormous advances in 20th century physics. Quantum mechanics described nature at microscopic scales. Albert Einstein's special relativity imposed the correct relationship between space, time, energy, and momentum. Quantum field theory brought quantum mechanics and special relativity into a common framework. Gauge symmetry helped determine the structure of fundamental interactions. Particle accelerators then tested the resulting predictions by creating conditions energetic enough to reveal particles that normally survive for only tiny fractions of a second. Over decades, these strands were gradually woven into what became known as the Standard Model. And so the history of particle physics contains a curious reversal. Scientists began with atoms because atoms looked fundamental. Then atoms opened to reveal electrons and nuclei. Nuclei opened to reveal protons and neutrons. Protons and neutrons opened to reveal quarks and gluons. Meanwhile, a confusing zoo of apparently unrelated particles turned out to contain families, symmetries, and repeated patterns. The deeper physicists looked, the longer the list became for a while. Then, rather unexpectedly, it began to shrink again. Beneath the particle zoo was a much smaller collection of elementary fields and particles, organized by a set of remarkably precise quantum rules. What initially looked like nature becoming more complicated was really nature slowly revealing its underlying order. The deeper particle physics goes, the less nature resembles a collection of tiny solid objects. At everyday scales, it is natural to imagine particles as extremely small pieces of matter, like microscopic grains moving through empty space. That picture can be useful for building intuition, but it is not the description used by modern particle physics. The Standard Model is a quantum field theory. In this view, the universe is filled with fields extending throughout space. There is an electron field, a quark field for each type of quark, an electromagnetic field, a Higgs field, and others. What we call a particle is a quantized excitation of one of these underlying fields. This idea emerged gradually from the quantum revolution of the early 20th century. In 1900, Max Planck found that the interaction between matter and radiation could be understood if energy was exchanged in discrete amounts rather than varying continuously in every circumstance. These packets became known as quanta. A few years later, Albert Einstein used the same general idea to explain the photoelectric effect. Light, which classical physics had described as an electromagnetic wave, could behave as though its energy arrived in discrete packets. Those packets would eventually be called photons. This was one of the first signs that nature did not fit neatly into the classical categories of particles and waves. Quantum mechanics developed rapidly over the following decades, replacing the idea of perfectly predictable microscopic motion with quantum states, wave functions, probability amplitudes, and measurable outcomes. An electron, for example, is not normally described as a tiny ball travelling along one perfectly defined path through an atom. Instead, its quantum state provides probabilities for the possible results of measurements such as position, momentum, or energy. The wave function is part of the mathematical description used to calculate those probabilities. It evolves according to quantum laws, but measurement does not simply reveal a hidden classical trajectory that was quietly there all along. Then another major problem appeared. Quantum mechanics had been developed largely for relatively slow particles, while Albert Einstein's special theory of relativity became essential when particles moved close to the speed of light. Paul Dirac helped bring these two frameworks together. In the late 1920s, Dirac developed a relativistic equation describing the electron. Remarkably, the mathematics contained solutions suggesting the existence of a particle with the electron's mass but opposite electric charge. That particle was the positron. The prediction of antimatter was an early sign that combining quantum mechanics with relativity was revealing something much deeper than a refined theory of tiny objects. It pointed toward quantum field theory. The distinction between a field and a particle is central. The electron field is not located only where an electron happens to be detected. The field is part of nature throughout space. An electron is an excitation of that field carrying specific properties, including electric charge, mass, and spin. A useful analogy is a vibration travelling through a larger medium, although the analogy should not be pushed too far. Quantum fields are not known to be mechanical substances vibrating inside some deeper material. They are fundamental ingredients of the theory itself. Particles are also divided into two broad categories according to a quantum property called spin. Spin is a form of intrinsic angular momentum, although it should not be pictured as a tiny sphere physically rotating around an axis. The matter particles of the Standard Model, including quarks and leptons, are fermions. They possess half-integer values of spin. The known force-carrying particles are bosons and possess integer spin. This difference has enormous consequences. Wolfgang Pauli formulated the exclusion principle, which states that identical fermions cannot occupy exactly the same quantum state. Electrons obey this rule. Inside an atom, they therefore fill different available quantum states, rather than all collapsing into the lowest one. This creates electron shells, helps determine the structure of the periodic table, and contributes fundamentally to the stability and variety of ordinary matter. Without the exclusion principle, chemistry would look radically different, assuming recognizable chemistry existed at all. Bosons behave differently. Satyendra Nath Bose developed a new statistical description of light particles, and Albert Einstein extended the same mathematics to material particles now called bosons. Unlike fermions, identical bosons can occupy the same quantum state in large numbers. This distinction helps explain phenomena ranging from laser light to Bose-Einstein condensates, where many atoms can enter a shared quantum state at extremely low temperatures. The Standard Model, however, is not only about the quantum behavior of individual fields, it is also about symmetry. During the 1950s, Chen-Ning Yang and Robert Mills developed a new form of gauge field theory. Their work provided mathematical foundations that would later become essential to descriptions of both the strong interaction and the unified electroweak interaction. Gauge symmetry is one of the defining ideas behind the Standard Model. At a broad level, a gauge symmetry says that certain changes in how a field is mathematically described must not alter measurable physics. When this symmetry is required to hold locally, meaning independently from place to place, additional interaction fields become necessary. Those fields are associated with force-carrying particles. The electromagnetic interaction is associated with the photon. The strong interaction is associated with gluons. The weak interaction is associated with the W and Z bosons. So the particles in the Standard Model are not an arbitrary collection that physicists happen to discover and place into a table. Their relationships are constrained by deeper symmetries. Their properties determine which interactions are possible, and the fields themselves provide the underlying stage on which particle creation, destruction, scattering, and decay occur. This changes the meaning of the familiar particle chart. It is tempting to look at its quarks, leptons, and bosons as though it were simply a periodic table of extremely small objects. But the real Standard Model is much richer. It is a theory of quantum fields, symmetries, and interactions. The particles are the observable excitations of those fields, and the universe, at its deepest experimentally tested level, seems less like a machine assembled from microscopic beads, and more like an intricate collection of quantum fields capable of producing particles whenever the conditions are right. If you stripped away almost everything complicated about ordinary matter, most of what remained would come from just a very small part of the Standard Model. The first generation of matter particles contains 4 members: the up quark, the down quark, the electron, and the electron neutrino. These are the lightest members of their respective families, and they are also the particles most closely connected with the stable matter around us. The up quark carries a positive electric charge equal to 2/3 of the magnitude of the electron's charge. The down quark carries a negative electric charge equal to 1/3 of that same magnitude. Those fractional charges may sound awkward at first, but they combine neatly inside familiar particles. A proton contains 2 up quarks and 1 down quark. The charges of those 3 quarks add together to produce the proton's overall positive charge. A neutron contains 1 up quark and 2 down quarks. In that arrangement, the positive and negative fractional charges cancel, leaving the neutron electrically neutral. So the 2 principal particles inside atomic nuclei are built from the same 2 fundamental quark types, simply arranged differently. But there is another important layer to the story. The quarks inside protons and neutrons are held together by the strong interaction, one of the fundamental interactions described by the Standard Model. That interaction is carried by gluons and is described by quantum chromodynamics. The strong interaction is so powerful at the scale of protons and neutrons that quarks are not normally found in isolation. Instead, they remain confined inside composite particles such as protons and neutrons. The force that binds protons and neutrons together inside atomic nuclei is related but slightly different. It is called the residual strong interaction. This is somewhat like the leftover effect of the deeper strong interaction operating between quarks. It allows nuclei containing multiple protons and neutrons to remain bound, despite the electrical repulsion between positively charged protons. Outside the nucleus, the electron takes over much of the story. The electron is an elementary lepton with negative electric charge. Unlike quarks, it does not experience the strong interaction. Instead, its behavior inside atoms is dominated by electromagnetism and quantum mechanics. Negatively charged electrons are attracted to positively charged atomic nuclei through the electromagnetic interaction, but electrons are not miniature planets travelling around nuclei on fixed little circular tracks. They occupy quantum states described by orbitals, which determine the probability of finding an electron in different regions around the nucleus. Those orbitals control much of chemistry. The arrangement of electrons determines how atoms interact, which chemical bonds they can form, how molecules behave, and how materials conduct or resist electricity. The hardness of a table, the transparency of glass, the reactions inside a battery, and the chemistry occurring in living cells all depend heavily on the quantum behavior of electrons. In a very practical sense, the texture of the ordinary world is largely an electron story. The fourth member of the first generation is much less noticeable. The electron neutrino has no electric charge and an extremely small mass. It interacts through the weak interaction and gravity, although gravity is far too weak to matter in most individual particle interactions. Electron neutrinos are produced in a wide range of processes. They appear in certain forms of radioactive beta decay. They are created in nuclear reactors. They are produced during nuclear fusion inside stars such as the Sun, and enormous numbers can be released during stellar explosions. Trillions of neutrinos from the Sun pass through a typical human body every second. Almost all of them continue onward without interacting with anything. They can pass through the entire Earth with surprisingly little difficulty, making them some of the most elusive particles in nature. The weak interaction also connects the particles of this first generation in an important way. A free neutron is not permanently stable. After an average lifetime of roughly 15 minutes, a free neutron can undergo beta decay. During this process, one of the neutron's down quarks transforms into an up quark through the weak interaction. The neutron therefore becomes a proton. The decay also produces an electron and an electron antineutrino, allowing electric charge, energy, momentum, and other conserved quantities to remain balanced. Inside many stable atomic nuclei, however, neutrons can survive indefinitely because the energy relationships are different. Protons, meanwhile, appear stable in every experiment conducted so far. Some speculative theories predict that they may eventually decay over unimaginably long timescales, but no proton decay has ever been confirmed. Electrons also appear stable. That stability matters enormously. If protons or electrons routinely disappeared, atoms would not remain intact for long. Instead, the stable first-generation particles provide a remarkably durable foundation for ordinary matter. And this brings us to one of the strangest facts hidden inside the Standard Model. There are 17 commonly counted fundamental particle types, yet almost every stable object you have ever touched is built primarily from just 3 of them. Up quarks and down quarks form protons and neutrons. Electrons surround the resulting nuclei. From those ingredients come atoms. From atoms come molecules. From molecules come oceans, rocks, atmospheres, cells, trees, animals, planets, and people. The electron neutrino is present too, but in a very different way, passing through the surrounding universe almost unnoticed. So although the Standard Model contains a much larger cast of particles, ordinary matter relies most heavily on a remarkably small trio: up quarks, down quarks, and electrons. Everything else adds interactions, transformations, heavier families, and deeper structure. But the familiar world begins with these. Once the first generation of matter is understood, the Standard Model becomes more puzzling rather than less. Nature seems to repeat itself. The second generation contains another set of 4 fermions: the charm quark, the strange quark, the muon, and the muon neutrino. Their roles resemble particles from the first generation. The charm quark has the same electric charge as the up quark. The strange quark has the same electric charge as the down quark. The muon has the same negative electric charge as the electron. The muon neutrino, like the electron neutrino, carries no electric charge. The difference is that these second-generation particles are heavier, sometimes much heavier. This repetition is one of the enduring curiosities of particle physics. The universe already appears perfectly capable of constructing stable atoms from up quarks, down quarks, and electrons. Yet nature contains an additional family following almost the same pattern. One of the earliest hints came from cosmic rays. During the 1930s, Seth Neddermeyer and Carl Anderson studied tracks left by energetic particles produced when cosmic rays struck Earth's atmosphere. They encountered a particle that looked strangely familiar. It carried the same electric charge as an electron, but it was far heavier. This was the muon. The muon has a mass a little more than 200 times greater than the electron, yet in many other respects it behaves like a heavier version of it. It belongs to the lepton family, does not participate in the strong interaction, and interacts through electromagnetism and the weak interaction. But unlike the electron, the muon is unstable. Its average lifetime is only about 2/millionths of a second. That sounds absurdly brief, although in particle physics it is actually long enough for muons created high in Earth's atmosphere to travel considerable distances before decaying. Special relativity helps them reach the surface because their high speed causes their measured lifetime to appear extended from our perspective. Eventually, a muon usually decays into an electron along with a muon neutrino and an electron antineutrino. The particle is therefore temporary, appearing naturally in high-energy environments and then quickly returning its energy to lighter particles. Its existence was famously unexpected. When physicist Isidore Isaac Rabi learned about the muon, he reportedly responded with the question, "Who ordered that?" The remark captured a genuine scientific problem. The electron clearly had an obvious role in atoms. The muon seemed like an unnecessary extra. The strange quark emerged from a different mystery. Experiments studying cosmic rays began revealing particles that behaved oddly. They could be produced rapidly in processes governed by the strong interaction, suggesting there was nothing especially reluctant about their creation. But once produced, they sometimes survived much longer than expected before decaying. Physicists described this unusual behavior using a property called strangeness. The eventual explanation was that these particles contained a new type of quark, the strange quark. Strong interactions preserve quark flavor in ways that allow strange particles to be produced efficiently, but their decay into lighter particles requires the weak interaction. Because the weak interaction is much weaker than the strong interaction, these particles can survive for comparatively long periods before decaying. The strange quark therefore became another member of the growing family of fundamental matter particles. Then came charm. During the 1960s, theorists were trying to understand why certain changes between quark flavors seemed to be strongly suppressed. Sheldon Glashow, John Iliopoulos, and Luciano Maiani proposed a mechanism involving an additional quark. That hypothetical particle became known as the charm quark. Charm was not added merely to make the particle table look symmetrical. Its presence helped explain why certain flavor-changing weak interactions occurred far less often than simpler models seemed to predict. Then, in 1974, experimental evidence arrived dramatically. A team led by Samuel Ting at Brookhaven National Laboratory discovered a new particle. At almost the same time, a team led by Burton Richter at the Stanford Linear Accelerator Center found the same state independently. The particle became known as the JPSI. Its unusually long lifetime for such a massive particle and its decay behavior pointed toward a bound state consisting of a charm quark and a charm antiquark. The discovery became so important that the period is sometimes called the November Revolution in particle physics. Charm had moved from theoretical necessity to experimental reality. The remaining member of the second generation is the muon neutrino. For a time, physicists did not know whether neutrinos associated with electrons and muons were truly different particles. That question was settled in 1962 at Brookhaven National Laboratory. Leon Lederman, Melvin Schwartz, Jack Steinberger and their colleagues produced a beam of neutrinos largely associated with muon processes and observed how those neutrinos interacted with matter. The neutrinos produced muons but not electrons in the expected way. This demonstrated that the muon neutrino was distinct from the electron neutrino. Nature therefore did not contain just one neutrino species, it contained families. Taken together, the charm quark, strange quark, muon and muon neutrino form a heavier copy of the first generation pattern. But they do not build stable everyday matter. Charm and strange particles decay into lighter states. Muons decay into electrons. Muon neutrinos can travel enormous distances, but they do not assemble into ordinary atoms. Second-generation particles are produced naturally when cosmic rays strike the atmosphere. They appear in radioactive and weak processes. They are routinely created in particle accelerators, but once the energy required to produce them is gone, they tend to decay toward lighter particles. The familiar universe therefore settles overwhelmingly into the first generation. This leaves a deceptively simple question. Why does the second generation exist at all? The Standard Model describes its particles extraordinarily well. It tells us how they interact, how they decay, and how their properties fit into the wider framework. But it does not explain why nature chose to repeat the same basic matter pattern with heavier masses. The second generation is therefore both familiar and mysterious. It looks like a heavier echo of ordinary matter. And somehow the universe decided that one echo was not enough. Nature repeats the pattern one more time. The third generation of matter particles contains the top quark, bottom quark, tau lepton, and tau neutrino. They follow the same basic charge pattern already seen in the first and second generations. The top quark carries the same positive fractional electric charge as the up and charm quarks. The bottom quark carries the same negative fractional electric charge as the down and strange quarks. The tau has the same negative electric charge as the electron and muon, while the tau neutrino carries no electric charge at all. But the third generation is much heavier, in some cases dramatically so. The tau lepton was the first member of this family to be identified. During the 1970s, Martin Pearl and a team working at the Stanford Linear Accelerator Center studied collisions between electrons and positrons. They observed unusual events suggesting the creation of a previously unknown heavy lepton. This particle became known as the tau. Like the electron and muon, the tau is electrically charged and does not participate in the strong interaction. But it is far heavier than either of them, with a mass more than 3,000 times greater than that of the electron. It is also extremely unstable. A tau typically survives for only a tiny fraction of a billionth of a second before decaying through the weak interaction into lighter particles. The next major piece arrived in 1977. At Fermi National Accelerator Laboratory, an experiment known as E288, led by Leon Lederman, detected a new particle state produced in high-energy collisions. The new state was called the upsilon. Its properties were best explained as a bound system containing a newly discovered quark and its antiquark. That quark became known as the bottom quark. The bottom quark is much heavier than the strange and down quarks that share its electric charge. It is unstable and normally appears only in short-lived particles produced in energetic environments such as accelerator collisions and cosmic ray interactions. The final quark in the Standard Model proved considerably harder to find. Once the bottom quark had been discovered, the structure of the theory strongly suggested that another quark should exist as its partner. This hypothetical particle became known as the top quark. But the top quark turned out to be extraordinarily massive. Its mass is roughly 173 billion electron volts. That is remarkable for an elementary particle. Expressed in familiar terms, the energy corresponding to a single top quark's mass is comparable to the mass energy of an entire tungsten atom, even though the top quark itself shows no confirmed internal structure. Producing such a heavy particle required extremely energetic collisions. The top quark was finally discovered in 1995 at Fermi National Accelerator Laboratory by two large experimental collaborations, the Collider Detector at Fermilab and D0. The discovery completed the six-quark structure of the Standard Model. The top quark is unusual even among quarks. Most quarks rapidly become incorporated into composite particles called hadrons. They combine with other quarks or antiquarks through the strong interaction before experimental detectors ever have a chance to observe them as anything resembling isolated objects. The top quark behaves differently because it decays extraordinarily quickly. Its lifetime is so short that it normally disappears through the weak interaction before the strong interaction can confine it inside a conventional hadron. This makes the top quark especially valuable to physicists. Many of its original properties can be inferred directly from the particles produced in its decay, without some of the complications introduced when other quarks become locked inside composite systems. The final member of the third generation is the tau neutrino. Its existence was expected because processes involving the tau appeared to require a distinct neutrino associated specifically with that lepton. But neutrinos are notoriously difficult to detect because they interact so weakly with matter. The first direct detection of the tau neutrino was announced in 2000 by the direct observation of the new tau collaboration at Fermi National Accelerator Laboratory. Researchers observed interactions in which incoming tau neutrinos produced tau leptons, providing direct evidence for the third neutrino flavor. With that result, the pattern became complete. 3 generations, each containing 2 quarks, 1 charged lepton, and 1 neutrino. Yet the third generation is not a stable foundation for ordinary matter. Top quarks decay rapidly. Bottom quarks decay. Tau leptons decay. The products of these decays tend to move through chains of weak interactions into progressively lighter particles. Eventually, much of the surviving matter ends up in the first generation, where stable electrons, up quarks and down quarks dominate the material universe. This might make the third generation sound unnecessary, but its particles are enormously important for testing the Standard Model. The top quark interacts very strongly with the Higgs field, making measurements of its properties especially valuable for understanding how elementary particles acquire mass. Bottom quarks and particles containing them provide sensitive tests of flavor physics, including the ways different quark types transform into one another. Their decays also allow physicists to investigate subtle differences between matter and antimatter. Tau particles and tau neutrinos provide further tests of whether all 3 generations really obey the same fundamental laws with perfect consistency. Any small departure from Standard Model predictions could point toward physics that has not yet been discovered. And this brings the 3 generations to one of their deepest mysteries. The Standard Model tells us that there are 3 known generations of fermions. It describes their interactions with extraordinary precision. But it does not explain why there should be exactly 3, nor does it explain the enormous differences in their masses. The electron is light, the muon is much heavier, the tau is heavier still. Among the quarks, the contrast becomes even more dramatic, culminating in the extraordinarily massive top quark. There is no simple pattern that predicts these masses from first principles within the Standard Model. They must be measured and inserted into the theory. So the third generation completes one of the most elegant patterns in particle physics, while making the puzzle even sharper. Nature seems to have created 3 versions of the same basic family. Only the lightest version is needed to build almost everything stable around us. The other 2 appear briefly in energetic environments, decay away, and leave behind a question the Standard Model itself does not answer. Why did the universe make 3 copies at all? Taken together, the quark family contains 6 known flavors. They are the up quark, down quark, charm quark, strange quark, top quark, and bottom quark. These 6 particles are divided across the 3 generations of matter. Up and down belong to the first generation, charm and strange to the second, and top and bottom to the third. They differ enormously in mass, but they share one particularly unusual feature. Their electric charges come in fractions. The up, charm, and top quarks carry a positive electric charge equal to 2/3 of the magnitude of the electron's charge. The down, strange, and bottom quarks carry a negative charge equal to 1/3 of that magnitude. And yet, despite decades of experiments, physicists have never found an isolated quark wandering around with a fractional electric charge. The reason lies in another property carried by quarks called color charge. Color charge has nothing whatsoever to do with ordinary color or visible light. Quarks are not literally red, green, or blue. Those names are simply labels physicists use for 3 possible varieties of the charge associated with the strong interaction. The theory describing this interaction is called quantum chromodynamics. Quantum chromodynamics governs quarks, gluons, color charge, and the strong interaction that binds quarks together. In some ways, color charge plays a role loosely comparable to electric charge in electromagnetism, but the strong interaction behaves very differently. One important rule is that the particles we observe freely in nature are color neutral. A proton, for example, contains 3 valence quarks arranged so that their combined color charge is neutral. The same is true of a neutron. Particles made from 3 quarks are known as baryons. Another important category is the meson. A meson consists primarily of a quark and an antiquark whose color charges combine into a neutral state. Pions and kaons are familiar examples. Together, baryons and mesons belong to the larger family of composite particles called hadrons. This explains why individual quarks are so difficult to imagine in isolation. They are subject to a phenomenon called confinement. Inside a proton or neutron, quarks are permanently bound by the strong interaction. If you try to pull 2 quarks farther apart, the interaction does not simply fade away in the manner we might expect from familiar forces. Instead, more energy becomes stored in the gluon field between them. Eventually, supplying enough energy does not release a lone quark. It becomes energetically favourable to create a new quark and antiquark pair. So rather than extracting one isolated quark, the system produces additional color-neutral hadrons. It is almost as though nature would rather create more particles than allow one quark to leave on its own. This behaviour is very different from electromagnetism. 2 electrically charged particles generally interact less strongly as the distance between them increases. The strong interaction has another surprising feature at the opposite extreme. When quarks are brought extremely close together, or examined at very high energies, their interaction becomes weaker. This property is called asymptotic freedom. David Gross, Frank Wilczek, and Hugh David Politzer discovered the theoretical basis of asymptotic freedom during the 1970s. At very short distances, quarks can therefore behave almost as though they are relatively free, even though they remain permanently confined when viewed across the larger scale of an ordinary proton or neutron. This helped make sense of experimental results that had already begun revealing something unusual inside protons. During deep inelastic scattering experiments at the Stanford Linear Accelerator Center, high-energy electrons were fired at protons. The way those electrons scattered suggested that the proton contained much smaller, point-like constituents. These constituents behaved in the manner expected of quarks. The experiments provided powerful evidence that protons and neutrons were not elementary particles after all. But even saying that a proton contains 3 quarks is only the beginning of the story. A proton has 3 valence quarks that determine important properties such as its electric charge and quantum numbers. 2 are up quarks, and 1 is a down quark. However, the interior of a proton is far more dynamic than 3 little particles sitting quietly beside one another. The strong interaction fills the proton with gluon fields. Those gluons continually interact with one another and with quarks. The proton also contains a fluctuating sea involving quarks and antiquarks arising within this strongly interacting quantum system. It is an intensely active object. This becomes especially important when considering mass. If the intrinsic masses of a proton's 3 valence quarks are simply added together, they account for only a small fraction of the proton's measured mass. Most of the proton's mass instead emerges from the energy associated with the strong interaction, including the motion of quarks and gluons and the energy stored in their quantum fields. Through Albert Einstein's relationship between mass and energy, that internal energy contributes to the proton's mass. This means that most of the mass in ordinary matter does not come directly from adding together the intrinsic masses of its elementary ingredients. Much of it emerges from the dynamics of the strong interaction itself. Under sufficiently extreme conditions, even confinement can take on a very different form. When atomic nuclei are collided at enormous energies, matter can briefly enter a state known as quark-gluon plasma. In this state, quarks and gluons are no longer confined inside separate individual protons and neutrons. Instead, they move within a hot, dense collective medium. Experiments involving energetic heavy ion collisions have recreated tiny droplets of this material for extraordinarily short periods. A similar state is thought to have filled the early universe during its first few microseconds, when temperatures were far too high for stable protons and neutrons to exist. As the universe expanded and cooled, quarks and gluons became confined into hadrons. Protons and neutrons emerged. Eventually those particles formed atomic nuclei, and much later electrons joined them to create atoms. So quarks are fundamental ingredients of ordinary matter, but they never build that matter alone. Their familiar forms emerge only through the collective behavior of the strong interaction. A proton is not merely three quarks. It is a living quantum system of quarks, gluons, fields, and energy, and almost every atomic nucleus in the visible universe depends on that remarkably restless structure remaining bound together. Leptons make up the other half of the Standard Model's matter particles. There are 6 of them in total. 3 are electrically charged: the electron, the muon, and the tau. The other 3 are neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. Like the quarks, leptons are arranged into 3 generations. The electron and electron neutrino belong to the first generation, the muon and muon neutrino to the second, and the tau and tau neutrino to the third. But leptons differ from quarks in one very important way. They carry no color charge. This means they do not participate in the strong interaction. Electrons, muons, and tau particles still experience electromagnetism because they carry electric charge, and all 6 leptons participate in the weak interaction. But the strong interaction that binds quarks inside protons and neutrons simply does not act on them. Among the charged leptons, the pattern is remarkably clear. The electron is the lightest and stable member. The muon is essentially a much heavier relative of the electron and survives for only around 2/millionths of a second. The tau is heavier still and disappears much more quickly. In each case, the particle carries the same negative electric charge. Then come the neutrinos, which are stranger in almost every respect. They carry no electric charge, possess extremely small masses, and interact so weakly with ordinary matter that enormous numbers can pass directly through planets without colliding with anything. The story of the neutrino began as an attempt to rescue one of physics' most fundamental principles. During beta decay, physicists observed electrons emerging from atomic nuclei with a range of different energies. If the electron were the only light particle leaving the nucleus, it looked as though some energy and angular momentum were simply disappearing. Wolfgang Pauli proposed a daring solution in 1930. Perhaps another particle was escaping unnoticed. It would have to be electrically neutral, extremely difficult to detect, and capable of carrying away the missing energy and angular momentum. Enrico Fermi later developed a theory of beta decay incorporating this new particle, and gave it the name neutrino, meaning roughly little neutral one. The idea worked beautifully. Detecting the particle was another matter. Neutrinos interact so rarely that for years it was unclear whether they could ever be observed directly. Frederick Raynes and Clyde Cowan eventually succeeded during the 1950s by placing a detector near a powerful nuclear reactor. Reactors produce enormous numbers of electron antineutrinos, and the sheer intensity finally made rare interactions measurable. The neutrino had gone from a theoretical bookkeeping solution to a detected particle. Its reluctance to interact remains one of its defining characteristics. The Sun produces neutrinos continuously through the nuclear reactions taking place in its core. Vast numbers stream outward, pass through space, cross Earth, and continue onward. Trillions of solar neutrinos pass through a typical human body every second, yet essentially none of them interact with us. Even an entire planet is surprisingly transparent to most neutrinos. For a long time, however, neutrinos seem to create another problem. Experiments designed to detect neutrinos from the Sun repeatedly found fewer electron neutrinos than solar models predicted. Either the models of the Sun were seriously wrong, the experiments were missing something, or the neutrinos themselves were behaving in an unexpected way. The answer turned out to be one of the most important discoveries in modern particle physics. Neutrinos can change flavour. A neutrino produced as an electron neutrino does not necessarily remain an electron neutrino forever. As it travels, its quantum state can evolve so that it may later be detected as a muon neutrino or tau neutrino. This phenomenon is called neutrino oscillation. Bruno Pontecorvo was among the first physicists to develop the idea that neutrinos might transform between different states. The concept eventually gained compelling experimental support. At the Super Kamiokande experiment in Japan, an enormous underground detector studied neutrinos produced when cosmic rays struck Earth's atmosphere. Takaaki Kajita and his colleagues found that the number and behaviour of atmospheric neutrinos depended on how far they had travelled. Neutrinos passing through Earth were changing flavour. The Sudbury Neutrino Observatory in Canada provided another crucial piece of the puzzle. Arthur MacDonald and his collaborators measured solar neutrinos in ways that could distinguish electron neutrinos from the total flux of all active neutrino flavours. The results showed that the Sun was producing approximately the expected number of neutrinos overall. They were not disappearing. Some had simply changed flavour before reaching Earth. This has a profound consequence. Neutrino oscillation requires neutrinos to possess non-zero masses and for the flavour states to be mixtures of different mass states. Yet, in the minimal original formulation of the Standard Model, neutrinos were treated as massless. The observation of neutrino oscillations therefore tells us that the simplest version of the Standard Model cannot be the complete story. Exactly how neutrinos acquire their masses remains unresolved. Their masses are known to be extraordinarily small compared with those of the charged leptons, but their exact absolute values have not yet been fully determined. Physicists are also trying to establish their mass ordering, meaning which neutrino mass state is the heaviest and which is the lightest. Another major question is whether neutrinos could be their own antiparticles, a possibility associated with particles known as Majorana fermions. Experiments also continue to investigate whether additional neutrino states might exist. One proposed possibility is the sterile neutrino, a hypothetical neutrino that would not participate in the ordinary weak interaction and would therefore be even more elusive than the three known flavours. No sterile neutrino has been conclusively established, so the neutrinos occupy a curious position within particle physics. They belong naturally within the Standard Model's family of leptons. They are produced constantly in stars, radioactive decays, nuclear reactors, cosmic ray collisions, and particle experiments. And yet their behaviour has already revealed that the most basic version of the Standard Model is incomplete. The particles that interact least with the rest of the universe may therefore be among the clearest hints that something deeper is still waiting underneath it. Light is one of the most familiar things in the universe, yet in the Standard Model it is associated with a single elementary particle, the photon. The photon is the quantum excitation of the electromagnetic field. It is also the particle associated with electromagnetic interactions, the force responsible for electricity, magnetism, light, atomic structure, and much of chemistry. Long before the photon became part of quantum theory, electricity and magnetism were studied as separate phenomena. During the 19th century, James Clerk Maxwell showed that they were deeply connected. Maxwell developed a unified classical theory describing electric and magnetic fields as different aspects of a single electromagnetic field. One of the great surprises of his work was that the equations predicted waves travelling through space at a particular speed. That speed matched the measured speed of light. Light, it turned out, was an electromagnetic wave. This was one of the most important unifications in physics. Electricity, magnetism, and light were no longer separate subjects. They were different expressions of the same underlying phenomenon. Quantum physics later added another layer. Light does not behave only as a continuous classical wave. Under many circumstances, electromagnetic energy is exchanged in discrete packets. Those packets are photons. A photon has no electric charge and has zero rest mass. In a vacuum, photons always travel at the universal speed of light. They cannot simply slow down in empty space in the way a massive particle can. When light passes through a material such as glass or water, its overall propagation through that material is slower because of interactions with the material. But individual photons between interactions still obey the fundamental laws governing light. The photon's lack of electric charge also means that photons do not directly respond to electric fields in the same way electrons do. Instead, photons interact with electrically charged particles. Electrons are especially important. An electron can absorb a photon, emit a photon, or change its quantum state through electromagnetic interaction. These processes help explain why atoms produce characteristic colors of light. When an electron in an atom moves from a higher energy state to a lower one, energy can be released as a photon. When an atom absorbs a photon with the right energy, an electron can move into a higher energy state. The same basic interaction appears again and again throughout the physical world. Reflection depends on electromagnetic interactions between light and matter. Chemical bonding depends on electromagnetic attraction and repulsion involving electrons and atomic nuclei. Electric currents involve the behavior of charged particles inside materials. Magnetism emerges from the motion and quantum properties of charged particles. Even the simple sensation of touching a solid surface depends heavily on electromagnetism. When your hand rests on a table, the atoms in your skin do not normally pass through the atoms in the wood. The negatively charged electrons in both materials interact electromagnetically, while the Pauli exclusion principle also restricts how electrons can share quantum states. What feels like solid contact is therefore largely the result of quantum mechanics and electromagnetism, rather than tiny hard objects physically pressing together like pebbles. The modern quantum theory describing electromagnetic interactions is called quantum electrodynamics. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga independently developed powerful mathematical methods that made this theory consistent and extraordinarily precise. Quantum electrodynamics describes how electrically charged particles interact with the electromagnetic field. It has become one of the most accurately tested theories in all of science. One famous example involves the magnetic properties of the electron. Quantum theory predicts a subtle quantity related to the electron's magnetic moment with astonishing precision. Experimental measurements and theoretical calculations agree to many decimal places. That level of agreement gives physicists enormous confidence that the electromagnetic part of the standard model is describing something very close to the underlying behavior of nature. There is, however, one common picture that should be handled carefully. It is often said that electromagnetic forces occur because charged particles exchange photons. This can be useful shorthand, but it should not be imagined as two particles continually throwing tiny glowing objects back and forth. In quantum field theory, interactions are described through the electromagnetic field and through probability amplitudes. In calculations, physicists often use Feynman diagrams containing internal lines described as virtual photons. These virtual photons are not the same thing as real photons traveling through space and being detected as light. A real photon can leave a source, travel through space, and arrive at a detector. A virtual photon is part of the mathematical structure used in perturbative calculations of interactions. Treating the two as identical physical objects can create more confusion than clarity. The photon also helps explain why electromagnetism has such a long reach. Because the photon has zero rest mass, the electromagnetic interaction is not restricted to a tiny distance in the way the weak interaction is. In principle, an electric field can extend indefinitely, although its strength usually becomes weaker with increasing distance and large collections of positive and negative charges often cancel one another. The weak interaction behaves very differently because its associated W and Z bosons are extremely massive. Their large masses help restrict weak processes to extraordinarily short distances. Electromagnetism, by contrast, can act across atoms, laboratories, planets, and even astronomical distances. Light from stars can travel through interstellar and intergalactic space for millions or billions of years before reaching a telescope. And all of that visible radiation is built from excitations of the same electromagnetic field responsible for the electrons inside atoms interacting with one another. This gives the photon an unusual place in the Standard Model. It is one entry in a relatively small particle catalogue, yet it is connected to an enormous portion of everyday experience. The colours we see, the warmth of sunlight, radio waves crossing space, the chemistry inside cells, the structure of atoms, electricity flowing through circuits, and the magnetic field surrounding Earth all belong to the electromagnetic world. Behind that enormous variety sits a quantum field, and its elementary excitation is the photon. Deep inside every proton and neutron lies one of the most powerful interactions known in nature. The strong interaction is described by quantum chromodynamics, the quantum field theory governing quarks, gluons, and color charge. At the center of that theory is the gluon. The gluon is the gauge boson associated with the strong interaction. In the same broad sense that the photon is associated with electromagnetism, gluons are associated with the force acting between particles that carry color charge. But the comparison only goes so far. Photons do not carry electric charge themselves. Gluons do carry color charge. That single difference makes the strong interaction much more complicated. The simplified Standard Model chart usually shows one entry labelled gluon, but there are actually 8 distinct gluon states. These arise from the possible ways color charge can be carried within quantum chromodynamics. Once again, the words used for color charge can be slightly misleading. Physicists refer to red, green, and blue color charges, but no visible colors are involved. These are simply convenient labels for different forms of strong interaction charge. Because gluons themselves carry color charge, they can interact directly with other gluons. Photons do not normally interact directly with one another in the same way, because photons carry no electric charge. This self-interaction among gluons is one of the reasons quantum chromodynamics has such unusual behavior. At ordinary hadronic scales, the strong interaction produces confinement. Quarks and gluons do not normally escape from protons, neutrons, and other hadrons as isolated particles. Attempting to pull quarks apart increases the energy stored in the strong field between them. Eventually, enough energy is available to create additional quarks and antiquarks, producing new hadrons instead of releasing a single free quark. Yet at extremely short distances, the behavior changes. The strong interaction becomes weaker. This property is called asymptotic freedom. David Gross, Frank Wilczek, and Hugh David Politzer developed the theoretical explanation for asymptotic freedom during the 1970s. At sufficiently high energies, quarks behave more nearly like independent particles, even though they remain confined when viewed over larger distances. This strange combination of freedom at short range and confinement at larger hadronic scales is one of the defining features of the strong interaction. There is also an important distinction between the fundamental strong interaction and the nuclear force that binds protons and neutrons together inside atomic nuclei. The fundamental interaction acts directly between quarks and gluons. Protons and neutrons are color neutral overall, yet they can still experience a leftover effect of the deeper strong interaction. This is called the residual strong interaction. It is somewhat analogous to how electrically neutral atoms can still exert electromagnetic forces on one another, even though their total electric charge may be zero. In nuclear physics, pions and other mesons provide a useful description of parts of this residual interaction between protons and neutrons. Pions are not fundamental force carriers in the Standard Model. They are composite particles made from quarks and antiquarks, but their exchange provides an effective description of how the residual strong interaction operates over the scale of atomic nuclei. Direct experimental evidence for gluons emerged dramatically in 1979. At the positron-electron tandem ring accelerator, operated by the German Electron Synchrotron Research Center in Hamburg, several experiments observed events containing three distinct particle jets. A jet is not a single fundamental particle travelling neatly through a detector. When an energetic quark or gluon is produced, confinement prevents it from appearing freely. Instead, it initiates a process that produces many hadrons travelling in roughly the same direction. The detector therefore records a spray of particles called a jet. In some electron and positron collisions, two jets could be understood as arising from a quark and an antiquark moving apart, but the appearance of three jet events provided evidence that an energetic gluon had also been emitted. The third jet carried exactly the kind of behaviour expected from the gluon, predicted by quantum chromodynamics. The strong interaction is enormously powerful at the scale of quarks and nuclei, but its most obvious effects are confined to very small distances because ordinary matter is organised into colour-neutral particles and nuclei. This is why you do not feel a strong interaction force pulling you toward a distant wall in the way gravity can act across a room. Its influence is concentrated deep inside matter, and that hidden influence accounts for an enormous fraction of the mass around us. The intrinsic masses of the quarks inside a proton or neutron contribute only a small part of the total. Most of the mass instead arises from the energy associated with quark motion and the strong gluon fields inside these particles. The strong interaction is therefore responsible for much of the mass of ordinary matter. This is an important correction to the common claim that the Higgs field gives everything its mass. The Higgs field plays a crucial role in giving elementary particles such as quarks and electrons their intrinsic masses, but the majority of the mass of a proton or neutron emerges from strong interaction energy. Since protons and neutrons account for almost all the mass of ordinary atoms, much of the mass in a human body, planet or star ultimately comes from quantum chromodynamics. The strong interaction also helps determine which atomic nuclei can exist. It binds protons and neutrons together closely enough to overcome the electromagnetic repulsion between positively charged protons at nuclear distances. Nuclear reactions inside stars depend on this balance. When light nuclei combine under the right conditions, differences in nuclear binding energy can be released. Those reactions help power stars and create many of the chemical elements. The iron in blood, the oxygen in the air, and the carbon in living cells all depend on nuclear processes whose behaviour is deeply connected to the strong interaction. So beneath the electromagnetic world of atoms and chemistry lies another layer. Atoms may be organised largely by electrons and photons, but their massive centres depend on quarks and gluons. The nucleus looks quiet from the outside. Inside, it is built from particles whose mass and stability arise from one of the most energetic quantum systems in nature. And holding much of it together is the gluon, a particle we never encounter in isolation, but whose influence is present in almost every piece of ordinary matter around us. The weak interaction is perhaps the least obvious of nature's fundamental interactions in everyday life. Gravity holds us to Earth. Electromagnetism gives us light, electricity, chemistry, and the solidity of matter. The strong interaction binds quarks inside protons and neutrons and helps hold atomic nuclei together. The weak interaction operates much more quietly, yet without it, radioactive decay would be profoundly different. Stars such as the Sun could not follow their familiar path of nuclear fusion, and many unstable particles would have no way to transform into lighter ones. The particles associated with this interaction are the W and Z bosons. There are two electrically charged forms of the W boson, one positively charged and one negatively charged, along with the electrically neutral Z boson. In the familiar count of 17 standard model particle types, the two charged forms are normally grouped together as the W boson family, rather than counted as separate entries. These particles are very different from the photon. The photon has zero rest mass. The W and Z bosons are extremely massive. The W boson has a mass of roughly 80 billion electron volts, while the Z boson is closer to 91 billion electron volts. That enormous mass is one reason the weak interaction operates only across extremely short distances, roughly a tiny fraction of the diameter of a proton. The weak interaction also has an ability that makes it especially important. It can change the flavour of particles. A down quark, for example, can transform into an up quark through a weak process. This is exactly what happens during one form of beta decay. A neutron contains one up quark and two down quarks. If one of those down quarks changes into an up quark, the neutron becomes a proton, which contains two up quarks and one down quark. During the process, a negatively charged W boson is involved briefly before producing an electron and an electron antineutrino. The W boson exists for such a short time that it never travels any appreciable macroscopic distance. Still, the transformation it enables has consequences extending from laboratory samples of radioactive material to the interiors of stars. Weak interactions are involved in the nuclear reactions that allow the sun to shine. At the beginning of the proton-proton chain, two protons ultimately produce a deuterium nucleus. For this to happen, one proton must effectively become a neutron through a weak interaction. Because the weak interaction proceeds comparatively slowly, the sun burns its nuclear fuel gradually rather than racing through it. That leisurely pace is one reason a star like the sun can remain luminous for billions of years. Weak interactions are also central to neutrino physics. Neutrinos participate in the weak interaction, allowing them to be created in nuclear reactions and occasionally detected when they collide with matter. During the collapse of massive stars and the resulting supernova explosions, vast numbers of neutrinos are produced through weak processes. These neutrinos carry enormous amounts of energy away from the collapsing stellar core and play an important role in the physics of the explosion. The weak interaction therefore earns its name from its relative strength, not from any lack of importance. For much of the 20th century, electromagnetism and the weak interaction appeared to be completely separate forces. Then a deeper connection emerged. Sheldon Glashow, Abdus Salam and Steven Weinberg developed what became known as electroweak theory. In this framework, electromagnetism and the weak interaction are not fundamentally unrelated. At sufficiently high energies, they are different expressions of a single electroweak interaction. The distinction visible in the low-energy universe appears because the underlying electroweak symmetry is broken. The Higgs field plays a central role in that breaking, leaving the photon massless while the W and Z bosons become heavy. The theory was elegant, but elegance alone is never enough. It had to make testable predictions. Gerardus Hooft and Martinus Veltman showed that the electroweak theory could be consistently renormalized, allowing physicists to make precise calculations without the mathematics collapsing under uncontrollable infinities. Then, experimental evidence began arriving. One important prediction involved weak processes mediated by the neutral Z boson. These were known as neutral current interactions, because particles could interact weakly without exchanging electric charge. In 1973, experiments at the European Organisation for Nuclear Research observed neutral current neutrino interactions. This was a major success for electroweak theory. But the W and Z bosons themselves still had to be found. That required far more energetic collisions. During the early 1980s, the superproton synchrotron at the European Organisation for Nuclear Research was converted into a proton-antiproton collider capable of reaching the required energies. Simon van der Meer developed techniques for accumulating and cooling intense antiproton beams, while Carlo Rubbia championed the experimental program and led the Underground Area 1 collaboration. In 1983, the Underground Area 1 and Underground Area 2 experiments reported the discovery of the W and Z bosons. Their measured properties closely matched electroweak predictions. Particles that had existed first as mathematical necessities had appeared in detector data. The weak interaction had already revealed another deeply surprising property decades earlier. It does not treat left and right as equivalent. Sung-Dao Lee and Chen-Ning Yang examined evidence suggesting that parity symmetry. The assumption that physical laws should behave identically in a mirror-reflected world had never actually been tested in weak interactions. They proposed experiments to find out. Chen-Shung Wu and her collaborators performed a famous experiment involving the radioactive decay of cobalt nuclei. The results showed that weak interactions violate parity. Nature can distinguish left from right. This remains one of the strangest features of the weak force, and it is built directly into the Standard Model. So the double U and Z bosons govern an interaction that rarely announces itself in ordinary experience. They allow quarks to change flavour. They participate in radioactive decay. They connect neutrinos with other particles. They influence supernovae, stellar fusion, and the gradual conversion of unstable matter into lighter states. And in the Sun, the weakness of this interaction helps ensure that nuclear transformation proceeds slowly enough for a star to shine steadily across immense stretches of time. The weak interaction may be quiet, but the universe would be almost unrecognizable without it. For all its elegance, electroweak theory once contained a serious problem. Gauge symmetry naturally produced force-carrying particles with no mass. That worked beautifully for the photon, which is massless. But experiments showed that the double U and Z bosons were anything but massless. They are extraordinarily heavy. Simply inserting masses into the equations by hand would destroy the mathematical structure that made the theory work. Physicists therefore needed a way for particles to behave as though they had acquired mass while preserving the underlying gauge symmetry of the theory. The solution involved a new quantum field. Today, it is called the Higgs field. Unlike many familiar fields, the Higgs field does not settle into a state with an average value of 0 when space is otherwise empty. Even the vacuum contains a non-zero Higgs field. This means that elementary particles moving through empty space are still interacting with something, not with a material substance in the ordinary sense, but with a quantum field that exists throughout the universe. The crucial process is known as spontaneous symmetry breaking. The underlying electroweak equations possess a symmetry, but the lowest energy state of the Higgs field does not display that symmetry in the same obvious way. A common analogy is a perfectly balanced object that could fall in any direction. The underlying situation is symmetric, but once one particular direction is selected, the final state no longer looks symmetric. In electroweak theory, this broken symmetry reorganizes the fields. The photon remains massless, the W and Z bosons acquire mass, and the mathematics remains consistent. Several physicists arrived at versions of this mechanism during 1964. Robert Brute and Francois Englert published one important formulation. Peter Higgs independently developed the idea and drew particular attention to an additional consequence. The field should possess a detectable quantum excitation. Gerald Guralnick, Carl Hagen, and Thomas Kibble also produced closely related work during the same year. Together, these developments established what became the Higgs mechanism. The particle eventually called the Higgs boson is not the Higgs field itself. That distinction is important. The Higgs field exists throughout space. The Higgs boson is a temporary excitation of that field, rather like how a photon is an excitation of the electromagnetic field. The Higgs field also interacts with elementary fermions. Quarks and charged leptons acquire masses through interactions described by quantities called Yukawa couplings. Broadly speaking, particles that couple more strongly to the Higgs field have larger masses. The top quark couples very strongly and is enormously massive. The electron couples much more weakly and is comparatively light. But the Standard Model does not explain why these coupling strengths have the values they do. They must be measured experimentally and inserted into the theory. This is one of the important limits hidden beneath the success of the Higgs mechanism. It explains how elementary particles can possess mass within the structure of the Standard Model. It does not explain why the electron has precisely its mass, why the top quark is so much heavier, or why the pattern of masses looks the way it does. There is also a common misunderstanding worth clearing away. The Higgs field does not directly account for most of the mass of ordinary objects. It gives intrinsic mass to elementary particles such as quarks and electrons, but protons and neutrons are composite particles. Most of their mass arises from the energy of the strong interaction, including the motion of quarks and gluons and the energy stored in the gluon fields inside them. Since protons and neutrons provide nearly all the mass of ordinary atoms, most of the mass in a person, planet, or star ultimately comes from strong interaction energy rather than directly from the Higgs field. Still, without the Higgs mechanism, the structure of the Standard Model would be radically different. The theory also made an unusually clear experimental prediction. If the Higgs field behaved as proposed, a Higgs boson should exist. Finding it was another matter. The Higgs boson is unstable and cannot simply be collected and examined. It must be created in sufficiently energetic particle collisions and then inferred from the particles into which it rapidly decays. For decades, increasingly powerful accelerators searched for it. Eventually, the Large Hadron Collider reached the required energies and produced enormous numbers of proton collisions. On the 4th of July 2012, 2 independent collaborations at the European Organisation for Nuclear Research announced evidence for a new boson. The ATLAS collaboration and the Compact Muon Solenoid collaboration had both observed signals near the same mass. The new particle had a mass of approximately 125 billion electron volts. It survived for only an extraordinarily tiny fraction of a second before decaying into other particles. The experimental teams required evidence corresponding to roughly 5 standard deviations before describing the observation as a discovery. In particle physics, this represents an extremely demanding statistical threshold intended to make random fluctuations extraordinarily unlikely explanations for the result. Further measurements showed that the new particle's properties matched those expected for the Higgs boson. In 2013, the Nobel Prize in Physics was awarded to Francois Englert and Peter Higgs for the theoretical discovery of the mechanism associated with the origin of mass for elementary particles. But discovering the Higgs boson did not finish the story. Physicists continue measuring how strongly the Higgs interacts with different particles. They study its decay channels, its relationship with the top quark, and whether its properties agree exactly with Standard Model predictions. One of the greatest remaining challenges is measuring the Higgs field's interaction with itself, which is connected to the shape of the field's underlying potential and may offer clues about the stability and history of the universe. Researchers also search for additional Higgs like particles or subtle deviations that might point beyond the Standard Model. So the Higgs boson occupies an unusual position. It completes the familiar list of 17 fundamental particle types. Its discovery confirmed one of the central ideas holding the Standard Model together. And yet the field associated with it leaves some of particle physics' deepest questions unanswered. The 17th particle closed one remarkable chapter in our understanding of nature. It also made the unanswered questions much harder to ignore. Antimatter sounds exotic, but it is not a speculative idea sitting at the edge of physics. It is built directly into the structure of relativistic quantum theory. The story begins with Paul Dirac. When Dirac developed a quantum equation for the electron that was compatible with special relativity, the mathematics produced an unexpected result. Alongside the familiar electron states, the theory also allowed solutions corresponding to a particle with the same mass as the electron but opposite electric charge. At first, this was deeply puzzling. But the implication was clear. If the mathematics was describing nature correctly, then there should exist a kind of mirror partner to the electron. That partner is the positron. More generally, every matter fermion in the Standard Model has a corresponding antiparticle. An antiparticle has the same mass and the same spin as its matter partner, but its electric charge and certain other internal quantum numbers are reversed. The electron has the positron, the muon has the antimuon, the tau has the antitau. Each quark has a corresponding antiquark, and each neutrino has an associated antineutrino within the standard model description, though the deeper question of whether neutrinos might in some sense be their own antiparticles remains unresolved. The positron was the first piece of antimatter to be discovered experimentally. In 1932, Carl Anderson was studying cosmic rays using a cloud chamber placed in a magnetic field. He observed a particle track curving in the opposite direction to an electron while showing the same mass. The simplest explanation was that the particle carried positive electric charge. The positron had been found. Antimatter had moved from mathematical prediction into physical reality. Since then, antiparticles have become routine features of particle physics. They are produced naturally in radioactive decays and cosmic ray collisions. They are created deliberately in particle accelerators. They also have practical medical applications. Positrons are used in positron emission tomography, where radioactive tracers produce positrons inside the body. When those positrons encounter electrons, the resulting signals can be used to construct detailed images of biological activity. The interaction between matter and antimatter is often described using the word annihilation. When a particle meets its corresponding antiparticle, they can transform into other particles. An electron and positron, for example, can annihilate and produce photons. This does not mean that matter simply disappears into nothing. Energy, momentum, electric charge, angular momentum, and other applicable conserved quantities must still balance. The original particle masses and their motion are converted into the energy and motion of the final particles. The reverse process can also occur. If enough energy is concentrated under the right conditions, that energy can produce a particle and its antiparticle. This is called pair production. A sufficiently energetic photon near a nucleus, for example, can contribute to the creation of an electron and a positron, provided energy and momentum are conserved. Matter and antimatter are therefore connected by the broader relationship between mass and energy. The early universe was energetic enough to produce particles and antiparticles in enormous numbers, and that leads to one of the deepest puzzles in modern physics. If the laws of nature treat matter and antimatter in such closely related ways, why does the observable universe appear to contain overwhelmingly more matter? Before reaching that mystery, antimatter itself is worth making a little less mysterious. Physicists can create entire antiatoms. At the European Organisation for Nuclear Research, experiments have produced antihydrogen. An ordinary hydrogen atom contains one proton and one electron. An antihydrogen atom contains one antiproton and one positron. Experiments such as the Antihydrogen Laser Physics Apparatus collaboration have trapped antihydrogen long enough to study its properties with increasing precision. Researchers can compare the spectral behavior of antihydrogen with ordinary hydrogen and investigate how antimatter responds to gravity. So far, these measurements are consistent with the expectation that matter and antimatter obey the same underlying physical laws to extremely high precision. It is also important not to confuse antimatter with dark matter. They are completely different ideas. Antimatter is made from antiparticles corresponding to the familiar particles of the Standard Model. Dark matter is the name given to an unknown form of matter inferred primarily from gravitational evidence. Ordinary antimatter interacts electromagnetically and can annihilate with matter. It does not provide a viable explanation for the invisible dark matter surrounding galaxies and galaxy clusters. The real mystery is not whether antimatter exists. It clearly does. The mystery is why there is so little of it around us. There are some known differences in the behavior of matter and antimatter. In 1964, James Cronin and Val Fitch discovered that decays of neutral kaons violate a combined symmetry known as charge parity symmetry. Charge symmetry involves replacing particles with antiparticles. Parity symmetry involves reflecting spatial coordinates as though viewed in a mirror. If both symmetries were perfectly preserved together, certain matter and antimatter processes would behave in exactly corresponding ways. The neutral kaon experiments showed that this combined symmetry can be violated. Nature contains a small preference in some weak interactions. This was a remarkable discovery because it offered at least one possible ingredient for explaining the matter-filled universe. Andrei Sakharov later identified 3 broad conditions needed to generate a lasting imbalance between matter and antimatter in the early universe. There must be processes capable of changing the amount of baryonic matter. There must be violations of symmetries that otherwise treat matter and antimatter too equally. And the universe must pass through conditions away from perfect thermal equilibrium. These are now commonly known as the Sakharov conditions. The Standard Model contains some of the required ingredients. It allows charge parity violation in weak interactions, and the early universe certainly experienced changing conditions as it expanded and cooled. But the known asymmetries appear far too small to explain the enormous dominance of matter that we actually observe. Some additional physics may therefore be required. This problem is known as baryogenesis, the attempt to understand how the early universe ended up with more matter than antimatter. It is one of the clearest examples of the Standard Model being simultaneously successful and incomplete. The theory naturally contains antiparticles. It predicts their properties. Experiments create them, trap them, and measure them. Yet when we look outward at stars, planets, galaxies, gas clouds, and ourselves, almost everything visible is made from matter rather than antimatter. The equations contain a remarkably elegant mirror population. The universe, for reasons we still do not fully understand, seems to have chosen one side of the mirror far more often than the other. The Standard Model becomes most useful when its particles stop being treated as a static list. Particles interact, they scatter, they transform, they decay. And all of those processes are described as changes in quantum fields governed by the symmetries, coupling strengths, and conservation laws built into the theory. A particle cannot simply turn into anything it likes. Every allowed interaction has rules. Electric charge must balance. Color charge must be treated consistently. Energy and momentum must be conserved. Spin matters. So do properties such as weak isospin, hypercharge, lepton number, baryon number, and flavor. Some of these quantities are familiar. Electric charge determines how strongly a particle participates in electromagnetism. Color charge determines whether it participates in the strong interaction. Flavor distinguishes particles such as up quarks from down quarks, or electrons from muons. Others are more abstract. Weak isospin and hypercharge are quantum properties used within the electroweak theory to organize how particles interact with the underlying electroweak fields. Together, they help determine familiar properties such as electric charge and which weak interactions are possible. Conservation laws are not simply convenient rules added afterward. Many arise from deep symmetries in nature. One of the most important results connecting these ideas was developed by Emmy Noether. Noether showed that continuous symmetries of physical laws are connected with conserved quantities. If the laws of physics do not change as time passes, energy is conserved. If those laws do not depend on where an experiment is performed in space, momentum is conserved. This relationship between symmetry and conservation is one of the foundations of modern theoretical physics. Within the Standard Model, possible interactions are often represented using mathematical objects that physicists draw as vertices. A vertex indicates that certain quantum fields can couple directly according to the rules of the theory. For example, an electron can interact with the electromagnetic field. A quark can interact with a gluon field. A weak interaction can allow one quark flavor to transform into another. Richard Feynman developed a diagrammatic method that became enormously useful for organizing these calculations. Feynman diagrams are now among the most recognizable images in particle physics. But they can also be misleading if taken too literally. They are not photographs of what particles are actually doing. They do not show tiny objects travelling along perfectly definite little paths. Instead, they are a bookkeeping system for terms in a quantum field calculation. Lines entering or leaving the diagram can correspond to particles in the initial and final states of an experiment. Internal lines represent mathematical intermediate contributions. These are often associated with so-called virtual particles, but the internal lines should not be imagined as directly observed particles briefly hiding between interactions. The complete physical prediction comes from combining all relevant quantum amplitudes. This matters because quantum mechanics works with probability amplitudes rather than ordinary probabilities at the earliest stage. Different possible processes can contribute amplitudes that add together. They may reinforce one another. They may partially cancel. This is quantum interference. Only after the relevant amplitudes are combined do physicists calculate probabilities for measurable outcomes. That is why a single particle collision can have several possible results, each with a different probability. The same logic governs particle decay. An unstable particle can transform into lighter particles if the interaction is allowed and if conservation laws can be satisfied. There must also be enough available mass energy for the final particles to be produced. Some particles are astonishingly stable. No decay of an isolated electron has ever been observed. Protons also appear stable in every experiment performed so far. Other particles disappear almost immediately. The muon survives for roughly 2/millionths of a second. The top quark lasts for only around a few 10 trillion trillionths of a second. The Higgs boson survives for an even shorter time, around a tiny fraction of a trillion trillionth of a second. These short lifetimes mean that such particles are not collected like grains of dust. Their existence is inferred from the particles produced when they decay. An unstable particle may have several allowed decay pathways. The probability associated with each pathway is described by a branching fraction. A Higgs boson, for example, can decay through several different channels. Some occur more often than others. By measuring those branching fractions and comparing them with standard model predictions, physicists can test whether the Higgs behaves exactly as expected. Lifetimes are also connected with quantum uncertainty. A very short-lived state naturally has a broader spread in its measured energy, or equivalently its reconstructed mass. This relationship between lifetime and energy width is a direct consequence of quantum mechanics. The shorter the lifetime, the broader the corresponding resonance tends to be. Making precise predictions for all of these processes requires more than just calculating the simplest interaction. Quantum field theory also includes corrections arising from additional possible interactions. These are called quantum corrections. A first approximation might describe a process using one simple diagram, while more precise calculations include increasingly complicated contributions. Some intermediate calculations can produce mathematical expressions that appear divergent. Renormalization is the framework that allows physicists to relate the parameters appearing in the theory to measurable quantities in a consistent way. It is not simply a trick for throwing away troublesome infinities. It is a systematic procedure for defining how quantities such as masses and coupling strengths depend on the scale at which they are measured. This leads to another important result. Interaction strengths are not always fixed numbers. They can run with energy. The effective strength of the electromagnetic weak and strong interactions changes as experiments probe different energy scales. The strong interaction, for example, becomes weaker at very high energies through asymptotic freedom. Electromagnetic interactions behave differently, becoming slightly stronger at shorter distances and higher energies. This means that nature can look subtly different when examined inside a high-energy collider than it does at ordinary laboratory scales. The basic laws remain the same, but the effective interaction strengths evolve. And this is what turns the standard model from a particle catalogue into a dynamic description of the universe. Its particles can be created when enough energy is available. They can collide. They can exchange energy and momentum. Unstable particles can decay. Quarks can change flavour through the weak interaction. Charged particles can emit and absorb photons. Quarks and gluons can form hadrons. Nuclei can fuse. Atoms can exchange photons and form chemical bonds. From a relatively small collection of fields and interaction rules comes an enormous range of physical behaviour. The 17 particle types matter, but the real richness lies in what they are allowed to do. The remarkable thing about the Standard Model is not simply that it describes a collection of particles. It is that those particles, together with the interactions between them, can eventually give rise to almost everything visible around us. The early universe began in conditions far hotter and denser than anything found naturally today. At those temperatures, matter did not exist in the familiar form of atoms, molecules, planets, or stars. Instead, the universe was filled with an extremely energetic mixture of particles and quantum fields. Quarks and gluons moved through a hot plasma. Electrons, neutrinos, photons, and other particles were abundant. Collisions were so energetic that particles could be created and destroyed continuously. As the universe expanded, it cooled. That cooling changed everything. Within roughly the first few millionths of a second, temperatures fell enough for quarks and gluons to become confined into composite particles. Up quarks and down quarks combined under the strong interaction to form protons and neutrons. This was an important turning point. Before then, the universe contained a quark-gluon plasma. Afterwards, stable hadrons such as protons became possible. The next major stage came during the first few minutes. This period is known as Big Bang nucleosynthesis. Temperatures had fallen enough for protons and neutrons to begin forming light atomic nuclei. Most of the ordinary matter that emerged consisted of hydrogen nuclei, which are simply protons. Significant amounts of helium were also produced, along with much smaller quantities of deuterium, helium-3, and lithium. The universe did not yet contain ordinary neutral atoms. It was still far too hot. Electrons moved freely through space, while photons repeatedly scattered from charged particles. Only hundreds of thousands of years later did the temperature fall enough for electrons to remain bound to nuclei. This period is known as cosmological recombination. Electromagnetism allowed negatively charged electrons to settle into bound quantum states around positively charged nuclei. Hydrogen and helium atoms became abundant. At roughly the same time, photons could travel much more freely because there were far fewer free charged particles available to scatter them. Radiation left over from this era is still observed today as the cosmic microwave background. Atoms were now present. But atoms alone do not make stars. For that, another fundamental interaction becomes essential: gravity. This introduces an important limitation. Gravity is not part of the Standard Model. The Standard Model describes the strong interaction, weak interaction, and electromagnetism, but the large-scale assembly of matter into stars, galaxies, and planets requires gravity, described separately by Albert Einstein's general theory of relativity. Over immense periods of time, gravity pulled gas into denser regions. As clouds of mostly hydrogen and helium collapsed, their centers became hotter and more compressed. Eventually, conditions inside the first stars became extreme enough for nuclear fusion to begin. Inside stars like the Sun, several parts of the Standard Model work together. The proton-proton chain begins with a weak interaction. Two protons approach one another, and one ultimately transforms into a neutron through a weak process. This allows the formation of deuterium. Further reactions then build helium. The weak interaction helps determine how slowly this first step proceeds, which is one reason stars like the Sun can shine steadily for billions of years instead of exhausting their fuel almost immediately. The strong interaction then becomes crucial in binding nuclei together. When light nuclei fuse into more tightly bound nuclei, differences in nuclear binding energy can be released. That energy eventually works its way outward through the star and emerges as radiation. Electromagnetism governs much of what happens to that radiation afterward. Photons interact with charged particles inside stars. Electromagnetic forces determine the structure of atoms once material cools. They govern chemical bonds, molecular shapes, electrical conductivity, thermal radiation, and nearly every chemical process associated with ordinary matter. The strong and weak interactions help build the nuclei. Electromagnetism turns those nuclei and their electrons into chemistry. Stars also create new elements. Fusion in stellar interiors builds elements such as carbon, oxygen, neon, silicon, and eventually iron in sufficiently massive stars. Elements heavier than iron require other processes. Neutron capture can build progressively heavier nuclei, while extreme environments such as supernova explosions and neutron star mergers can produce many of the heaviest elements found in nature. Gold, uranium, and other heavy nuclei therefore owe their existence to violent astrophysical events occurring long before the formation of Earth. Those elements are eventually scattered through space. Later generations of stars and planets form from material enriched by earlier stars. Rocky worlds can then contain silicon, iron, magnesium, oxygen, carbon, and many other elements produced through cosmic nuclear history. On a planet such as Earth, electromagnetism takes on another role. Atoms combine into molecules, carbon forms complex chemical structures, hydrogen and oxygen form water, proteins, nucleic acids, lipids, and countless other biological molecules arise through electromagnetic interactions among electrons and nuclei. The Standard Model does not explain biological evolution. It does not explain consciousness. It does not independently explain why the universe began in the conditions it did. But it describes much of the microscopic behavior of the ingredients from which biological systems are made. Another quiet but essential rule is the Pauli exclusion principle. Because electrons are fermions, identical electrons cannot all occupy the same quantum state. This helps produce the layered electron structure of atoms, it supports the periodic table, it contributes to the stability of matter. At far higher densities, the same underlying principle produces electron degeneracy pressure. Inside white dwarf stars, electrons are compressed so tightly that quantum mechanics resists further compression. Electron degeneracy pressure can support a white dwarf against gravitational collapse, at least up to a certain mass. So a rule governing elementary fermions can help determine the fate of entire stars. This is the deeper meaning behind the idea that 17 particles built everything. Not every particle serves as a literal brick. Most stable ordinary matter is made primarily from up quarks, down quarks, and electrons. Photons carry electromagnetic radiation. Gluons bind quarks. W and Z bosons govern weak transformations. The Higgs field contributes to the masses of elementary particles. Neutrinos stream through stars, planets, and space. The heavier generations appear briefly in energetic environments and decay away. What matters is the complete system. A small set of particles and fields, following quantum rules, can combine into protons and neutrons. Those become nuclei. Nuclei join electrons to become atoms. Atoms become molecules. Gravity gathers matter into stars and planets. Stars create new elements. Chemistry becomes increasingly elaborate. And from that enormous ladder of complexity, the visible universe emerges. The ingredients are surprisingly few. The possibilities are almost unimaginably large. To test a theory built around particles far smaller than anything we can see directly, physicists need machines capable of creating conditions that ordinary matter almost never experiences. The largest of these machines is the Large Hadron Collider. It is a circular particle accelerator roughly 27 kilometers around, buried underground near Geneva and crossing beneath the border region between France and Switzerland. The collider is operated by the European Organization for Nuclear Research, an international laboratory created to allow countries to work together on fundamental physics. Its purpose is not simply to make particles move quickly. It is to concentrate enormous amounts of energy into extremely small collisions and then study what emerges. Inside the accelerator, protons travel through two separate beam pipes in opposite directions. The pipes are maintained at an ultra-high vacuum, so the beams can travel without constantly striking gas molecules. Powerful superconducting magnets guide the protons around the circular tunnel. These magnets must be cooled to extremely low temperatures so that their electrical resistance becomes effectively negligible, and they can generate the intense magnetic fields required to bend such energetic beams. Radio frequency cavities provide repeated pushes to the protons, gradually increasing their energy. By the time the beams are ready for collision, the particles are travelling extraordinarily close to the speed of light. The combined collision energy can approach roughly 14 trillion electron volts. That number does not mean a single proton becomes enormously massive in the ordinary sense. Most of the extra energy is associated with its motion. When two high-energy protons collide, however, part of that collision energy can be converted into the mass and motion of entirely new particles. This is one of the most direct consequences of mass-energy equivalence. Heavy particles that do not normally exist in stable matter can therefore appear briefly in the debris of a collision. The top quark can be created, W and Z bosons can be produced, Higgs bosons can appear. These particles often survive for unimaginably short periods, but their decay products leave measurable traces. The collider therefore acts less like a microscope with a lens, and more like a controlled reconstruction of extremely energetic particle interactions. Several enormous detectors surround the points where the beams collide. ATLAS and the compact muon solenoid are the two largest general-purpose experiments. Both study a wide range of phenomena, including Higgs bosons, top quarks, electroweak interactions, strong interaction processes, and possible evidence for particles not included in the standard model. The two experiments overlap deliberately in many of their goals. If both independently observe the same phenomenon using different detector designs and analysis methods, confidence in the result becomes much stronger. The Large Hadron Collider Beauty experiment has a more specialized purpose. It focuses particularly on particles containing bottom and charm quarks. These particles provide sensitive tests of flavor physics and allow researchers to compare subtle differences between matter and antimatter. Rare decays are especially interesting because processes that occur only occasionally can sometimes reveal effects from particles or interactions too heavy to be produced directly. The Large Ion Collider experiment studies another extreme state of matter. Instead of focusing only on proton collisions, it examines collisions between heavy atomic nuclei. These collisions can create tiny droplets of quark-gluon plasma, a hot state in which quarks and gluons behave collectively rather than remaining confined inside individual protons and neutrons. Similar conditions are thought to have existed during the earliest moments of the universe. None of these detectors simply takes a photograph of a collision. A particle interaction can involve dozens or hundreds of detectable products, and many particles disappear before travelling any measurable distance. The detectors therefore work in layers. Tracking systems measure the curved paths of electrically charged particles as they pass through magnetic fields. From the curvature, physicists can infer properties such as charge and momentum. Calorimeters absorb many particles and measure their energies. Different layers are designed to respond to different kinds of particle. Muon chambers sit farther outward because muons can penetrate through material that stops many other particles. Neutrinos usually escape the detector entirely, so their presence must be inferred from missing momentum and energy. The result is a kind of forensic reconstruction. A Higgs boson, for example, is not normally seen directly. It is identified statistically through combinations of particles that match known Higgs decay patterns. This makes collider physics enormously demanding. Proton collisions occur at tremendous rates, and the overwhelming majority do not contain rare new phenomena. Trigger systems rapidly decide which events are worth saving for detailed analysis. Computing networks then process enormous quantities of data. Detector behavior must be calibrated continuously. Background processes must be modeled carefully. Statistical methods are used to determine whether an apparent signal represents genuine physics or an ordinary fluctuation in the data. Independent analyses are repeated. Different decay channels are compared. Different experiments check one another. The most famous result of this process came in 2012. Atlas and the compact muon solenoid independently found evidence for a new boson with a mass of roughly 125 billion electron volts. Its properties were subsequently shown to match those expected for the Higgs boson. The discovery completed the particle content required by the Standard Model in its familiar form. But finding new particles is only part of what the Large Hadron Collider does. Much of modern collider physics is precision physics. The Standard Model makes extremely specific predictions about how frequently certain processes should occur, how particles should decay, and how their properties should be distributed. Researchers can therefore search for new physics without necessarily discovering an entirely new particle. A known particle might decay slightly more often than expected. A particular distribution of collision products might have an unusual shape. The Higgs boson might interact with another particle at a strength slightly different from the Standard Model prediction. A tiny discrepancy, if confirmed repeatedly, could be the first sign of a deeper theory. This is one reason precise measurements of top quarks, double, U, and Z bosons, Higgs bosons, particles containing heavy quarks and strong interaction processes matter so much. The Standard Model has survived an extraordinary number of tests. Every successful measurement narrows the space in which alternative theories can hide. Organizations such as the Particle Data Group play an important role in this effort. The group gathers measurements from experiments around the world, evaluates their consistency, and produces widely used summaries of particle masses, lifetimes, decay probabilities, interaction strengths, and other properties. These compilations provide something close to a continuously refined reference map of known particle physics. At the same time, many ideas proposed to extend the Standard Model have not appeared in collider data. No confirmed supersymmetric particle has been found. No convincing evidence for additional spatial dimensions has emerged. Straightforward candidates for weakly interacting dark matter have not been discovered at the collider. This does not prove that all such ideas are wrong. Some predicted particles may simply be too heavy, too rarely produced, or too difficult to distinguish from ordinary backgrounds. But their absence matters. It tells physicists that many of the simplest versions of these theories cannot be correct. The next stage of the collider program is designed to push precision even further. The High Luminosity Large Hadron Collider aims to produce far more collisions than the original program. Higher luminosity means more opportunities for rare events to occur. A process happening once in many billions of collisions becomes much easier to study when the total number of collisions increases dramatically. This will allow much more precise measurements of Higgs interactions, rare Standard Model processes, and possible tiny deviations from established predictions. In a curious way, the Large Hadron Collider has made particle physics both more complete and more mysterious. It found the Higgs boson. It confirmed the Standard Model across an extraordinary range of energies. It has measured known particles with steadily increasing precision. And yet it has not revealed the obvious new layer of physics that many researchers once hoped would appear quickly. Dark matter remains unexplained. Gravity remains outside the Standard Model. The origin of neutrino masses is still uncertain. The matter-antimatter imbalance remains unresolved. The strange pattern of particle masses and generations still lacks a deeper explanation. So the collider has not shown that the Standard Model is the final theory of nature. It has shown something almost more intriguing. The Standard Model works extraordinarily well. And the better we test it, the more carefully any deeper theory will have to hide. For all its extraordinary success, the Standard Model is not a complete description of nature. That is not because the theory routinely fails. Quite the opposite. Its predictions have survived decades of increasingly precise experiments. The particles it describes have been found. Their interactions occur with the expected strengths. The Higgs boson appeared where the theory said something like it should. Measurements from particle colliders repeatedly agree with calculations to remarkable precision. And yet there are major parts of the universe that the Standard Model simply does not explain. The most obvious omission is gravity. Albert Einstein's general theory of relativity describes gravity not as an ordinary force passing between particles, but as the curvature of space-time produced by matter and energy. This works extraordinarily well on scales ranging from planets and stars to black holes and the expanding universe. The Standard Model, meanwhile, is built using quantum field theory. Trying to combine these two frameworks into one consistent description has proved exceptionally difficult. No experimentally confirmed quantum theory of gravity currently exists. Physicists sometimes speak of a hypothetical particle called the graviton, which would represent a quantum of the gravitational field in certain approaches, but no graviton has ever been detected. String theory offers one possible framework in which gravity can emerge naturally alongside quantum physics. Loop quantum gravity takes a very different approach by attempting to quantize the geometry of spacetime itself. Other ideas continue to be explored. None has yet been experimentally established as the correct quantum description of gravity. Then there is dark matter. Astronomical observations strongly suggest that galaxies and galaxy clusters contain far more gravitating matter than can be accounted for by stars, gas, dust, planets, and the known particles of ordinary matter. Dark matter appears to outweigh ordinary matter by roughly 5 to 1. Fritz Zwicky noticed an early version of this problem while studying the motions of galaxies inside the Coma cluster. Decades later, Vera Rubin and Kent Ford measured the rotation of spiral galaxies and found that stars far from galactic centers were moving much faster than expected if visible matter were providing most of the gravitational attraction. A large amount of unseen mass seemed to be present. Additional evidence now comes from gravitational lensing, galaxy clusters, the cosmic microwave background, and the growth of large-scale cosmic structure. But no known standard model particle provides a convincing explanation for the dominant dark matter inferred from these observations. Neutrinos have mass and barely interact with ordinary matter, which initially makes them sound promising, but the known neutrinos are too light and move too quickly to account for most dark matter. Dark energy presents an even larger mystery. During the late 1990s, teams studying distant exploding stars found evidence that the expansion of the universe is accelerating. The work associated with Saul Perlmutter, Brian Schmidt, Adam Ries, and their collaborators transformed modern cosmology. The name dark energy is now used for whatever is responsible for this accelerated expansion. Its underlying nature remains unknown. When the cosmic inventory inferred from modern observations is considered, ordinary matter made from standard model particles contributes only a small fraction of the total matter and energy content. Most appears to lie in dark matter and dark energy, neither of which has a confirmed explanation within the standard model. Even among the particles the model already contains, difficulties remain. Neutrinos provide a particularly clear example. The minimal original standard model treated neutrinos as massless. But neutrino oscillations demonstrate that at least some neutrino mass states must have non-zero mass. The theory therefore requires extension. Exactly how neutrinos acquire those masses remains unsettled. It is not known whether they receive mass through the same basic Higgs mechanism as charged fermions, whether additional particles are involved, or whether neutrinos might possess a more unusual type of mass, connected with the possibility that they are their own antiparticles. The matter-antimatter imbalance remains another major unanswered question. The standard model includes differences between matter and antimatter through charge parity violation, but the amount of known violation appears insufficient to explain why the observable universe contains an enormous abundance of matter and almost no corresponding large regions of antimatter. Something seems to have tipped the early universe in favour of matter. The full mechanism behind that imbalance has not been identified. There are also problems that arise from the internal structure of the theory itself. One is known as the hierarchy problem. The electroweak scale associated with particles such as the W boson, Z boson, and Higgs boson is vastly lower than the energy scale where quantum gravity is expected to become important. Quantum corrections to the Higgs mass make this enormous separation difficult to understand naturally without some additional mechanism or deeper structure. Another mystery is the strong charge parity problem. Quantum chromodynamics appears capable in principle of allowing a form of charge parity violation in the strong interaction. Yet experiments indicate that any such effect must be extraordinarily small. The standard model can accommodate this by choosing a particular parameter to be extremely close to zero. What it does not explain is why nature would choose such an incredibly tiny value. One proposed solution introduces a hypothetical particle called the axion, which has also become an interesting dark matter candidate. Then there are the numbers themselves. The standard model contains parameters that must be learned from experiment rather than derived from the theory. Particle masses are among them. So are mixing angles and several interaction parameters. The theory can describe what happens once these values are supplied. It does not tell us why the electron has its particular mass, why the top quark is enormously heavier, or why neutrino masses are so tiny. It does not explain why there are exactly 3 generations of matter. It does not tell us why the pattern repeats at all. The vacuum presents another enormous puzzle. Quantum field theory associates quantum fields with vacuum energy. Straightforward estimates of that energy differ catastrophically from the small effective energy density associated with the observed acceleration of the universe. This mismatch is known as the cosmological constant problem and is often described as one of the largest disagreements between naive theoretical expectation and observation anywhere in physics. The very early universe raises still more questions. Cosmic inflation is the idea that the universe underwent a period of extremely rapid expansion early in its history. Inflation helps explain several observed features of the cosmos and provides a mechanism for producing the primordial fluctuations from which galaxies eventually developed. But the identity of whatever field or mechanism drove inflation has not been established. Many models introduce quantum fields beyond those contained in the standard model. There is also the remarkable stability of the proton. No proton decay has ever been observed. Within the standard model, the proton is effectively stable because of the structure of its allowed interactions, but many grand unified theories predict that quarks and leptons are connected at a deeper level and that protons should eventually decay over immensely long timescales. Experiments continue looking. A confirmed proton decay would be an unmistakable sign that the standard model is part of something larger. The search for that larger structure takes many forms. Grand unified theories attempt to combine the strong, weak and electromagnetic interactions into a single framework at extremely high energies. Supersymmetry proposes a deeper relationship between fermions and bosons. Other ideas involve composite versions of particles currently considered elementary, additional Higgs fields, axions, sterile neutrinos, hidden sectors, and particles that interact only very weakly with known matter. So far, none has been confirmed as the correct extension. The search is not limited to one enormous collider. Experiments such as the Deep Underground Neutrino Experiment and Hypercamia-Candé are designed to probe neutrino behavior with extraordinary precision. Underground dark matter detectors search for rare interactions from unknown particles passing through Earth. Antimatter experiments compare matter and antimatter ever more precisely. Gravitational wave observatories test gravity under extreme conditions. Future particle colliders may examine Higgs bosons, electroweak physics, and possible new particles at still greater precision or energy. And new physics may not announce itself by producing an enormous unfamiliar particle. It could first appear as something much quieter, a decay occurring slightly too often, a particle property differing subtly from its predicted value, a neutrino behaving in an unexpected way, a tiny statistical discrepancy that refuses to disappear as more data accumulate. That possibility captures the unusual position of the standard model. It is not considered incomplete because it is a bad theory. It is considered incomplete because it is an astonishingly good theory describing a domain that we already know cannot be the whole story. Its 17 particle types provide one of the clearest maps of fundamental nature ever created. But gravity remains outside the map. Dark matter has no confirmed place on it. Dark energy is barely represented at all. The origins of particle masses, generations, neutrino properties, and the matter-filled universe remain partly unexplained. The map is extraordinarily detailed where it has been drawn. It is the blank space around the edges that has become impossible to ignore. And somewhere within those blank regions may lie the next layer of fundamental physics. The 17 particles that built everything are not really 17 tiny pieces from which the universe is assembled like a box of microscopic bricks. The deeper picture is far more interesting. The Standard Model describes a system of quantum fields. Some of those fields give rise to matter particles. Others are associated with the fundamental interactions. And one, the Higgs field, helps explain why many elementary particles possess mass. The familiar count begins with 6 quarks. There is the up quark, the down quark, the charm quark, the strange quark, the top quark, and the bottom quark. Then come the 6 leptons. The electron, the muon, the tau, the electron neutrino, the muon neutrino, and the tau neutrino. Together, these 12 particles are arranged into 3 generations. The first generation contains the up quark, down quark, electron, and electron neutrino. This is the generation that dominates the stable matter around us. Up quarks and down quarks combine to form protons and neutrons. Electrons surround atomic nuclei. Electron neutrinos are produced in nuclear reactions, radioactive decays, stars, and other weak processes, usually passing through matter almost unnoticed. The second generation repeats the same basic pattern with heavier particles. The charm quark mirrors the electric charge of the up quark. The strange quark mirrors the down quark. The muon resembles a heavier electron. The muon neutrino accompanies it as a second neutrino flavour. Then nature repeats the pattern again. The third generation contains the top quark, bottom quark tau, and tau neutrino. The top quark is particularly remarkable because its mass is roughly comparable to that of an entire tungsten atom, despite the fact that no internal structure has ever been confirmed inside it. The heavier generations do not make stable ordinary atoms. They appear in energetic environments, particle collisions, cosmic rays, and radioactive processes, and they rapidly decay toward lighter states. Yet their existence tells us something profound. Nature does not seem to have created only the particles required to build ordinary matter. It created 3 generations following the same underlying structure. The Standard Model describes that pattern very well. It does not explain why the pattern exists. Alongside the 12 fermions come the particles associated with 3 of nature's fundamental interactions. The photon belongs to electromagnetism. It is the quantum excitation of the electromagnetic field and is associated with interactions involving electrically charged particles. Every beam of visible light, every radio signal crossing space, every electromagnetic interaction holding electrons within atoms, and much of the chemistry occurring around us ultimately belongs to this same electromagnetic framework. The gluon belongs to the strong interaction. Gluons interact with quarks and with one another through color charge. They help confine quarks inside protons, neutrons, and other hadrons. Although a simplified particle chart often presents the gluon as a single entry, quantum chromodynamics contains 8 gluon states. The double U and Z bosons belong to the weak interaction. The double U bosons are electrically charged. The Z boson is neutral. These particles are enormously heavier than the photon and operate across extremely short distances. The weak interaction allows particles to change flavour. It enables beta decay. It plays a central role in neutrino interactions. It contributes to the processes occurring in supernovae. And inside stars such as the Sun, weak interactions help initiate the nuclear reaction chain that ultimately produces the light-warming Earth. so the weak interaction may deserve its name in terms of comparative strength, but certainly not in terms of cosmic importance. Then there is the Higgs boson. The Higgs boson is the detectable excitation of the Higgs field, a quantum field with a non-zero value throughout empty space. Through the Higgs mechanism, the W and Z bosons acquire their masses. Quarks and charged leptons also acquire their elementary masses through interactions with the Higgs field, with different coupling strengths corresponding to different particle masses. But this must be stated carefully. The Higgs field does not directly provide most of the mass of an ordinary human body, planet, or star. The intrinsic masses of quarks do depend on their interaction with the Higgs field. But protons and neutrons are composite particles, and most of their mass comes from the energy of the strong interaction. Quarks move within them. Gluon fields carry enormous amounts of energy. Quantum chromodynamics binds the entire system together. Through the equivalence between mass and energy, this strong interaction energy accounts for most of the mass of protons and neutrons. And since atomic nuclei provide almost all the mass of ordinary matter, much of the mass in the visible world emerges from the dynamics of quarks and gluons rather than directly from the Higgs field. This makes the journey from 17 particle types to the world around us much more subtle than simply stacking particles together. Begin with up quarks and down quarks. The strong interaction confines them inside protons and neutrons. Those protons and neutrons can bind together through the residual strong interaction to form atomic nuclei. Electrons then occupy quantum states around those nuclei. Electromagnetism binds the atoms together internally. The Pauli exclusion principle organizes electrons into different available states, helping create atomic shells and the structure behind the periodic table. Atoms then interact electromagnetically with other atoms. Chemical bonds form. Molecules emerge. Some molecules remain simple, others become extraordinarily elaborate. Water forms. Carbon combines with hydrogen, oxygen, nitrogen, phosphorus, sulfur, and other elements. Eventually, under the right conditions, chemistry becomes rich enough to support the self-replicating and evolving systems associated with life. Before any of that can happen, however, the elements themselves must exist. The earliest universe produced mostly hydrogen and helium nuclei, along with much smaller quantities of a few other light nuclei. Gravity, which lies outside the standard model, gathered matter into stars. Inside those stars, nuclear fusion created heavier elements. Massive stars built nuclei through successive stages of fusion. Supernovae and neutron star mergers provided environments capable of creating many still heavier elements through neutron capture processes. The carbon in living cells, the oxygen being breathed somewhere on Earth tonight, the calcium in bone, and the iron in blood all have histories stretching back into earlier generations of stars. Eventually, gravity gathered enriched material into new stars and planets. Rocky worlds formed, atmospheres developed, chemistry unfolded, and on at least one planet, the interactions among particles described by the Standard Model became organized into organisms capable of discovering that the particles existed at all. Reaching this picture took more than a century of experiments. Joseph John Thomson revealed the electron. Ernest Rutherford, Hans Geiger, and Ernest Marsden exposed the atomic nucleus. James Chadwick discovered the neutron. Carl Anderson found the positron. Cosmic ray observations revealed unexpected particles arriving naturally from energetic processes above Earth. Accelerators created conditions that could be controlled and repeated. Deep inelastic scattering showed that protons contained smaller point-like constituents. Neutrino experiments revealed particles able to travel through enormous amounts of matter while interacting only rarely. Particle colliders discovered the W and Z bosons. Experiments found the top quark. Neutrino observatories showed that neutrinos oscillate between flavors. Then the Large Hadron Collider produced the Higgs boson, completing the familiar particle content predicted by the Standard Model. Each discovery required instruments capable of reaching farther beyond direct human perception. Cloud chambers revealed tracks, bubble chambers recorded collisions, underground detectors watched for neutrinos. Enormous particle detectors reconstructed particles that existed for fractions of a second too small to imagine comfortably. Today, experiments such as ATLAS and the compact muon solenoid surround collision points where protons meet at energies of trillions of electron volts. The resulting debris is measured, reconstructed, and compared with standard model calculations. And again, the theory works. This is perhaps the most important point to appreciate. The standard model is not merely a rough outline. It is one of the most precisely tested frameworks ever developed in science. Quantum electrodynamics predicts electromagnetic phenomena with extraordinary accuracy. Quantum chromodynamics describes the behavior of quarks and gluons. Electroweak theory correctly predicted particles and interactions that were later discovered. Measurements of particle masses, decay rates, branching fractions, interaction strengths, and collision outcomes repeatedly agree with the model. The discovery of the Higgs boson was especially striking because the theoretical mechanism behind it had been developed decades before the required particle could finally be produced and detected. And yet, after all of that success, the standard model remains incomplete. Gravity is not contained within it. Albert Einstein's general theory of relativity describes gravity through curved spacetime. But a confirmed quantum description of gravity remains missing. Dark matter is another enormous absence. Observations of galaxies, galaxy clusters, gravitational lensing, and the cosmic microwave background strongly indicate the existence of unseen matter beyond the ordinary matter described by the standard model. Dark matter appears to outweigh ordinary matter by roughly 5 to 1. No known standard model particle explains it satisfactorily. Dark energy is even more mysterious. The expansion of the universe is accelerating, yet the underlying cause remains uncertain. Neutrinos present another clue. The minimal original standard model treated neutrinos as massless. Neutrino oscillations prove that at least some neutrino mass states possess non-zero mass. The mechanism producing those masses is still not fully understood. Then there is antimatter. The standard model contains antiparticles naturally. It permits subtle differences between matter and antimatter through charge parity violation. Yet those known effects do not appear sufficient to explain why the observable universe contains so much matter and so little antimatter. The masses of the particles themselves remain mysterious too. The theory tells us how to use those masses once they are measured. It does not tell us why they take the particular values they do. Why is the electron so light? Why is the top quark so enormously heavy? Why are neutrinos lighter still? Why are there 3 generations? Why do the coupling strengths have their particular values? Why does the strong interaction appear to preserve charge parity to such extraordinary precision? The standard model describes the patterns. It does not yet explain why nature chose those patterns. And perhaps that is the most interesting way to think about the 17 particles. They are not necessarily the final answer. They are the smallest confirmed vocabulary with which modern physics can describe the visible material world. 6 quarks, 6 leptons, the photon, the gluon, the double U boson, the Z boson, and the Higgs boson. From those fields and particles come protons and neutrons. From protons, neutrons, and electrons come atoms. From atoms come molecules. From nuclear reactions come stars and chemical elements. From those elements come planets. And from sufficiently elaborate chemistry, living systems can emerge. A list that fits comfortably on a single page can therefore describe ingredients present in oceans, mountains, atmospheres, stars, galaxies, and every living cell. But around that compact vocabulary remain large areas of silence. Gravity, dark matter, dark energy, neutrino masses, the matter-antimatter imbalance, the unexplained hierarchy of particle masses. Possibly entire particles and fields that have never yet appeared in an experiment. The 17 particles of the Standard Model may therefore be less like the final inventory of nature and more like the first page of a much larger catalogue. They have already shown that extraordinary complexity can emerge from remarkably simple ingredients. And if history is any guide, what currently looks fundamental may one day turn out to be part of an even deeper structure. For now, though, these 17 particle types remain our clearest experimentally tested description of the quantum ingredients underlying the visible universe. A very small collection, an astonishing set of rules, and, from them, almost everything we have ever known.